Thanks. So as always with the recording, now that I've started the recording, you can type your name into the chat. Nothing that was typed in before the recording gets saved. So at this point, please type your name into the chat so we'll have a record for your attendance for data. Um, Deborah, if we're out of data money after today, I need to talk about how I can get the funding to you because my bank changed and they won't do SendWave anymore. So I now need a different way, either MoneyGram or Wise or something, Western Union, whatever. But I mean, ideally, it would be something that you can do on a mobile phone. So maybe we can talk at the end and just figure out what's the best way to keep the transfers. I'm very annoyed at my bank for basically it went off of MasterCard, and that means that I can't use SendWave anymore. So, all right. In any case, we'll figure that out at the end. Okay.
Yeah, sure.
All right. Sounds good. So let me mute everybody. Okay, so welcome again to this class. It's been 2 weeks, so I want to spend some time doing review, and there were also a lot of homework exercises. I think I only got one solution from James. I didn't get any other solution papers, so I want to spend some time going over the questions to make sure everybody understands before we move on. And just a reminder about scheduling, we have this week and then next week, December 11th, and then the week after that, December 18th. And December 18th will be the last meeting of the semester before the holiday break, and we'll start back up in January. It's possible we might change the time. I'm going to send out a survey after December 18th to see if people like this time or if they would rather meet on Fridays or later or earlier. So, I mean, if everybody says all different things, then we'll just keep this time. But if there's a consensus in favor of changing the time, then you know we can talk about changing it for January. But for the rest of December, these last three meetings will all be at the usual time on Thursdays at 4:30. Okay, great. So welcome everybody. Once again, please put your name in the chat if you haven't done so already, and we'll make sure that you get your data for all of the upcoming weeks. Okay, good. So let's recall what we were talking about since it's been 2 weeks. We've been talking about oh, this is not the what did I want to do? Oh, yes, that's right. Okay, I wanted to just recall these things about combinatorics that we were talking about because they'll be important for solving the homework problems. So, if you remember how we counted things in combinatorics, the main thing that we did was to talk about this multiplicative principle of independent events. This was the most important technique that we have for counting things up in combinatorics. And so, just to recall, we saw this before that if we have an event that's conditioned on making a number of independent choices, what does independent means? It means that no matter how you make the choice, there's the same number of possibilities for all of your other choices. Nothing, making one choice will not affect how many possibilities there are for your other choices. Okay, so if something is conditioned on making a number of independent choices, and for each choice there are a certain number of options, then our main principle is that the total number of possible choices is the product of the number of choices at each step, right? So this is what the main technique we've been using. Independent means what I just said. It means the number of choices at each step is not affected by any particular choices made at the previous steps. So the basic example, which we always have, I should just say, let me let me actually just erase this. This doesn't make that much sense out of context. So I'll cross this out. And then the other thing that we saw is that sometimes you have to make your choices in a particular order in order to make them independent. So this was our general multiplicative principle of how to do combinatorics, how to count things. You take the big thing you want to count and you break it up into a bunch of little pieces and you multiply all of the numbers of possibilities together. And the other thing to recall is sometimes events are not independent. So sometimes you have different events that you're working with that are not independent of each other. And one way to deal with non-independent choices is to do a case-by-case analysis. And if you want to use fancy language, this is known as the additive principle for counting disjoint events. And what does it mean? It means that if the number of objects that you're asked to count can be split up into two or more non-overlapping categories, this is what we'll call cases, then we can add up the number of objects in each category to get our final answer. Okay, and this is going to be important. This is going to be used on the homework. So we'll need to use this on some of the homework problems. Okay, so you're going to need to use this on some of the homework problems. And the other thing that I want to review is that we talked about these permutations and combinations. So we have these two numbers, NPK. By the way, sometimes you'll also see this. Another notation for this is PNK, and another notation for this is CNK. Different books use different notations. They're all fine. You can use the one that you want. Um, and so what are these numbers? What do they count? Well, if you have a row of K seats and you want to fill them one person in each seat from a group of N people, and you want to know how many possible arrangements are there to do that, then that number of arrangements is what's called PNK or NPK, and it's given by this formula, n factorial divided by n minus k factorial. And then a similar question, which asks if there's n students in a classroom, how many ways can you form a committee of them? But you don't care about the order, you just care about who's on the committee. So, how many ways can you choose k of the students out of n of them? Then the answer is this number that we call CNK or NCK, or sometimes this is written n choose k. I'll say this is sometimes said n choose k. And this is given by this similar formula involving factorials. It's almost the same as the formula for NPK. We have an n factorial divided by an n minus k factorial, but there's an extra k factorial in the denominator. That's the extra. That's what makes the combinations different from permutations. So as a word, this is just to recall, these are called permutations because the order matters. So when you permute the order, that counts as a different arrangement. And this is called combinations. And for combinations, the order doesn't matter. Okay. So, so this is basically what I want to recall so that doing the homework makes sense. Okay, so we need to know this law of independent probability, the multiplicative principle. We need to know the additive principle for dealing with non-independent events by splitting them up into cases. And we need to know what permutations and combinations are. Okay, so with that all in mind, let's go over the homework questions. There's 5 questions, so it may take a little bit of time, but I want to make sure that everybody understands these questions because very few people submitted answer sheets. So I want to make sure that everybody is up to speed so that we can talk about things today and it will make sense. Okay, so the homework questions start off pretty simple. So the first thing is how many 3-letter words start with a vowel? And for the purposes of this question, a word is any sequence of 3 letters. So it doesn't have to be an actual word. Okay, so EZQ counts as a word. So how many 3-letter words start with a vowel? This is going to be a classic example of the multiplicative principle. Okay, so we have a 3-letter word, so I usually like to write out three things. The way this question is phrased, choosing each letter is an independent event, right? I'm not saying that the letters can't repeat or that they affect each other in any way. We have maybe some conditions on the individual letters, but none of the conditions on one letter affect any of the conditions on the other letter. So choice, I'm just going to write that the choice of each letter is independent. So we can use the multiplicative principle. Okay, so to use the multiplicative principle, we need to know how many choices we have for each letter. So who wants to, can somebody tell us how many choices we have for each letter?
Can it be three?
Yes. So James, yep.
Yeah. Can it be three? Three choices?
Well, we're going to make three different choices exactly. So for the first letter, how many different choices can we make for the first letter? So the question says it's three-letter words.
Yeah,
It has to start with a
26.
vowel.
26 choices
Right. I guess,
we
yeah, it's a little ambiguous. What are our vowels? Do we count Y or not? I think I'm gonna say for the purpose of this question, Y is not a vowel. Okay. For the purposes of this question. So what do we have? A, E, I, O, and U.
yeah.
Right. So it's five choices for the first, right? So we have five choices for the first letter because it has to be a vowel. And then the second and third letters, we have no conditions on them at all. So how many choices do we have for them?
Should we say 26?
26? Exactly. So 26 choices for the second letter and 26 choices for the third letter because we're using the multiplicative principle, so we just multiply them all together. So if you multiply these all together, you get 676, so you're going to get 33, 80. So this is the answer over here. Okay, and I mean, how many of them are actual words? Well, that depends on what a word is. That makes it a little bit less of a math question, more of an English question. But for our purposes in this question, it's just 3380. And so it's a straightforward application of the multiplicative principle. Five choices for the first letter, 26 for the second letter, 26 for the third letter, and there is no interaction between the letters. The choices are completely independent. It doesn't matter whether I choose an A, an E, or an I for the first letter. I'll still have 26 choices for the second letter, no matter what choice I make for the first letter. Okay, so this is kind of straightforward application of the multiplicative principle. Okay, so any questions about this one? This should be pretty clear. Okay, good. Okay, no questions for this one. Let's move on to the next one. So homework exercise 2. How many three-letter words are there that contain at least one vowel? Okay. So this is a little less straightforward because if I have again, it's a three-letter word, then what I'm going to say is that the letter choices are not independent here. Why are the letter choices not independent? Well, we want to know how many three-letter words are there that contain at least one vowel. So let's say I make my first two choices. Well, if neither one is a vowel, then my third choice has to be a vowel, which means I'll only have five choices. But if instead I make these choices and one of them is a vowel, then my third choice could be anything, and I'll actually have 26 choices, right? So whether I need to put a vowel in that last spot or not depends on what I've already chosen in the first two spots. And what that means is that these choices are not independent. We can't uh, we can't um, we can't just find a number of choices for each letter and multiply them together. Okay, that's not going to give us the correct answer. Okay, so this is a very important concept to understand is that this is not independent, and that's what makes it a little bit more difficult than than the previous problem, which is all where everything is independent. Okay, so does that make sense that we can't just go ahead and use the multiplicative principle? Okay, So there's two ways to do this. The first way would be to try to break it up into cases. Maybe the first one's a vowel or it's not, and then break that up into subcases. You can do it that way, but I think it's a little bit harder. So the
Uh,
technique that, yeah, sorry, yes,
that
James?
the consonant and that are the vowel.
Right.
So there are
So
21, 21
21,
consonants.
right. Yeah. So 21 consonants. Mhm. So
Yeah.
what do we do with 21? So what do we want to count? What do we do with 21 consonants?
The three-letter words with no vowel in
Right.
is one.
Right. Exactly. So what we're going to do is we're going to count the wrong thing. We're going to count the three-letter words with no vowels and then subtract this.
With three-letter word with at least one vowel.
Right. So we're going to subtract this from the number of total, or from the total number of three-letter words. Total number of three-letter words. Right? And this gives the number of three-letter words with at least one vowel. Right? Because if I take the total number of three-letter words and I subtract the ones with no vowels, then the ones that are left all have at least one vowel. So, so first, let's maybe calculate what is the total number of three-letter words if we have no conditions at all. So what's the total number of three-letter words? That's going to be here. So total number of three-letter words.
8,315.
Yep. And then we're going to subtract over here, which is three-letter words with no vowel. And this is going to give us our final answer. So, and the good thing about this is that these are all independent things. Three-letter words, total number, you can just choose each letter by itself. Three-letter words with no vowel, again, it's totally independent. Each letter needs to be a consonant, so it doesn't matter which one you pick. So, what's the count for the first one? How do we do the total number of three-letter words with no conditions at all? Anyone? Okay, well, this is not so hard,
Yeah,
right? Because this here, everything
Yeah,
is
that's the one.
independent, right? Yeah, yeah, Linford.
Yeah, is that 21, please?
So, which one are we doing? The ones with no vowel or just the total number of three-letter words?
The one with no vowel.
No vowel over here. Okay, we can do this one first, right? So there's 21 consonants. So how many three-letter words are going to have no vowel? Or like what expression will give us that? So yes, there's 21, right? We've 21 choices for the first letter. And then how many choices for the second letter? Well, the second letter also has to be a consonant, right? So we'll also have 21 choices here. And for the third letter, same thing, 21. It's 21 choices for each of the three letters. Okay. And then now for the total number of three-letter words, that has no constraints at all, right? So for the first letter, we actually have a total of how many choices? How many choices for the first letter? Well, you can be any letter at all, right? So we have 26 choices. And then for the second letter, we also have 26 choices. And for the third letter, we also have 26 choices. So the total number of words, three-letter words, is 26 times 26 times 26. And the total number of three-letter words with no vowel is 21 times 21 times 21. And if we take the difference of those, that exactly will give us the number of three-letter words that have at least one vowel. So I'm just going to calculate what that is, right? So 26 cubed minus 21 cubed. Turns out that this is equal to 8,315. Okay. So it's very important that you understand what is our logic here, right? The logic is it's hard to count words with at least one vowel by doing the letters individually because choosing the letters is not independent. If you don't choose vowels here, then you need to choose a vowel here. If you do choose vowels here, then you don't need to choose a vowel here. But all of this, if then, that means dependence. That means you can't just use the multiplicative principle. So instead, you can turn this into a problem that takes two different outcomes, both of which you can use the multiplicative principle for. Total number of three-letter words with no vowel. Both of these can be calculated with the multiplicative principle because all your choices are independent. And then you can subtract them to get the total number of three-letter words that has at least one vowel. Okay. In this case, you get 8,315 is the answer. All right. Any questions here? Okay. Can I please explain it over? Okay. So let's look over here, right? So there's 21 consonants. So this is a technique that we did. Is there an alternative step for this? Yeah, there is an alternative way to do it, but the alternative way is harder. Okay. So let me explain this way one more time, and then I can try to do the alternative way. Okay. So first thing to know is that there's 21 consonants. There's 21 letters that are not vowels. Okay. So what does it mean that a word contains at least one vowel? If a word contains at least one vowel, that means it doesn't have no vowels, right? The opposite of having at least one vowel is having no vowels, right? So if you know how many words have no vowels, then you know the total number of words that have at least a vowel. Because let me maybe draw a picture, right? Here we have this is a picture. This circle represents all three-letter words. And now I'm going to divide this down the middle. This here is going to be words with no vowels. And this here is going to be words with at least one vowel. Right? And these two parts make up the entire circle because every word has either no vowels or has at least one vowel. Right? So let me say if I call this quantity A and this quantity B, and then the total quantity of all three-letter words, if I call this C, then we have that A plus B is equal to C. Right? And well, we want the words with at least one vowel, A. So in this case, A is equal to C minus B. And this is what we'll calculate. Okay, so now the point is the words with at least one vowel is the total number of words minus the words with no vowels. And what's the point of doing this? The point is that C and B by themselves are much easier to calculate than A. Okay, C is just all three-letter words. That's an easy question. It's 26 times 26 times 26, right? You just want to know every possible three-letter word. B is also easy. You want three-letter words with no vowels. So that means all three choices are consonants. And you have 21 choices for each of the three letters. So you get 21 times 21 times 21. So you have to take 26 times 26 times 26 and subtract 21 times 21 times 21, and you're left with the answer that you actually want, which is this words with at least one vowel. Okay, and so we see the numbers done over here. This is what we were calling C. It's the total number of three-letter words. And this is what we were calling B, the three-letter words with no vowels. And when you subtract them, this is when you put it in a calculator, this is what you end up getting as the answer. Is that more clear? Does anybody have a follow-up question? Okay. Okay, let's move on. Okay, so, all right, exercise 3. So this one's a little harder. So how many three-letter words can be formed from the letters in bubble? And the hint is we need to split into cases depending on how many B's there are. So now, again, this is something where um, it's not independent. Okay, so if I take my three letters here, not independent, for instance, if I choose a U, I can't choose it again because there's only one U. But if I choose a B, I can choose it again. Okay. Right? So for instance, if I choose a B, then I have four choices for the next letter. But if I choose a U, then I only have three choices for the next letter. So this violates independence. So that means we can't just use the multiplicative principle of probability because depending on which letter I choose first, I have a different number of choices for what to take second. Okay, so James says four cases, which is correct. So instead, we're going to have to do this by cases. And the cases are the cases depending on how many B's there are. So James sees you could do, well, maybe I'll do it in this order. There could be three B's, two B's, one B, or no B's. Right? These are all the choices. Right? You could have three B's, two B's, one B, or no B's. So let's see what happens. Let me see if I can just do these all separately. So this is going to be three B's, two B's, one B, and zero B's. Okay. All right. Because you could choose up to three B's, right? So if you're going to choose three B's, how many three-letter words can you make? This one's very easy. Well, if there's three B's, right? The only word that you can make is BBB. That's the only word with three B's, right? So in this case, we have only one choice, which is BBB. It's the only one that you can make. Okay. Let's skip two B's for now. Two B's is actually maybe the hardest case. So let's look at what happens if you have one B Well, actually, 1B is maybe also the harder. 2 and 1 are harder. Let's go to no B's first. That's going to be the next easiest one. So for no B's, that means we have the U, the L, and the E. So that's three different letters, and we want to know how many different three-letter words we can make from that. Well, if you've got the U, the L, and the E, and you want to put it in any order, this is exactly the permutations, right? So you have three available letters, which are U, L, and E, and you're making a three-letter word. So what this actually is 3p3, right? Because it's the number of ways you can arrange three things from a total of three objects, which is 3p3, which if you go back to the formula, that's 3 factorial divided by 3 minus 3 factorial, and that's 6 over 1. You have to remember that 0 factorial equals 1, and that means there's going to be six choices. Okay, so the number of ways to do this with no b's at all is there's going to be six ways. Okay, because it's just choosing the letters U, L, and E and somehow permuting them. All right. Questions on this so far? Okay. So now let's do two B's. So what happens when you have two B's? Well, the third letter, so you can phrase this as making two choices. And your two choices are the first choice is which letter is not B. Well, we have three choices for that, right? It could be either the first letter, the second letter, or the third letter. Sorry, let me this up. And then the second choice is what is that letter? For this, there's also going to be three choices because that letter could be U, L, or E. So to make a three-letter word that has two B's, you can view this as being independent, two independent choices. You first choose which letter is not going to be the B, and then you choose which letter is that actually going to be. And in each case, you have three choices. So what that means in total is that you're going to have 3 times 3 equals 9 choices in this case. So we have 9, we got 6, we've got 1. Okay, so do we understand how we made this as we were able to view this as two independent choices? One independent choice is which letter, which space is not going to have the B. And the second independent choice is what letter will you put in that space? And those two choices tell you all of the ways you can make a three-letter word from bubble with two B's. Okay? So there's 9 choices here. So lastly, we're going to have how many ways of doing it with one B? Okay, and doing it with one B, similarly, we'll have number one, instead of which letter is not the B, we'll have which letter is the B. Again, that's going to be three choices. It can be the first, the second, or the third letter. And then for the other two letters, once you put the B, you have two more letters, and you've got to choose them from a list of three letters, and the order matters. And so we'll say how to choose the other two letters. The other two letters. So how do we choose the other two letters? And the answer to this is it's going to be permutations, right? Because you have two spaces, two letters to choose out of a possibility of three letters, U, L, and E, and the order matters. So the way that we choose the other two letters is going to be 3p2, which is going to be 3 factorial over 3 minus 2 factorial. And this again is equal to 6 over 1, which is equal to 6 choices. So total, we get 3 times 6 equals 18 choices. Okay, so this question's a little bit complicated, right? We have to do all of these different cases. And then once you're in all of the individual cases, well, some of the cases are easy, like when you have 3Bs, and some of the cases are not so bad, like when you have 0Bs. But when you have 2Bs or 1B, you're making really two different choices. You're first choosing where to put the Bs, and then you're choosing what letters to put in that are not Bs. Okay? So which letter is not a B and what is that letter? Three choices each. 3 times 3 is 9. Which letter is the B? That's three choices. And how to choose the other two letters? That's a permutation of two things out of a group of three. So that's 3P2, and that's equal to 6. So you end up getting 3 times 6, which is 18 choices. So for the final answer, you have to add up all of the cases together. And this is going to give you all of the words. Every word's going to have either 3Bs, 2Bs, 1B, or no B. So you're going to have 1 plus 9 plus 18 plus 6. It's going to turn out to be 34 words. Let me put this on the next page. So total count is thus equal to 1 plus 9 plus 18 plus 6, which is equal to 34 words. Okay. I'll go back over here. Right. So this is a harder question than the last couple. The next question will actually be easier. But I wanted to go through this slowly so that everybody understands. We have to do cases because it's not independent. And then with each case, sometimes we do have two different independent events that we're using to multiply together to get the amount of choices for that case. Okay. Any questions? Okay. Okay, let's go to the next question then. Okay, the next one's actually a little easier, so that's good. So exercise 4. An ice cream shop has 7 flavors and 10 toppings. In how many ways can a bowl of ice cream with 2 flavors and 2 toppings be chosen? So in this case, we are going to have 2 independent choices. Right? We can choose the flavors and we can choose the toppings. Right? We can choose the flavors and we can choose the toppings. So that means that we can use the multiplicative principle. Okay? So we need to know how many ways can we choose the flavors and how many ways can we choose the toppings. And we have formulas that we've talked about with permutations and combinations that will tell us how to do that. So how many ways can we choose 2 flavors out of 7 possibilities? Or what is this a question of combinations or is it a question of permutations? You want to choose a way to choose two flavors out of a choice of seven. Anybody? Well, we've got seven choices. Choosing two flavors out of seven is the same thing as choosing two students out of seven. Doesn't matter that it's ice cream flavors instead of students. It's the same question, right? So choosing two flavors out of seven, right? This is going to be seven, choose two, right? You're choosing two. It doesn't matter what order you pick the flavors in. It's the same bowl of ice cream, right? But we have seven, choose two, which if you go back to our formulas for binomial coefficients, this is 7 factorial divided by 2 factorial times 7 minus 2 factorial. And that's 7 factorial divided by 2 factorial times 5 factorial. You can use a calculator for this if you want. You can multiply out 7 factorial if you want, but what's probably more useful here is to do cancellation, right? So this is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by, well, 2 factorial is just 2, and then 5 factorial is 5 times 4 times 3 times 2 times 1. So if you want to do this by hand, this makes, oh, no. Sorry about that. Um, Sorry. Okay, here we are. No. Uh, okay, so combination, exactly, right? So you get this fraction over here, and now you have lots of cancellations, the ones and the twos and the threes and the fours and the fives. And what you're left with is just 7 times 6 divided by 2. So that's just 42 divided by 2, and that's equal to 21. Okay. Okay. So the number of ways of choosing the flavors is there's 21 different ways to choose two flavors out of 10. Two flavors out of seven. Okay, it's combination, as James says. So this is a combination. Okay. Okay, what about toppings? Well, it's the same question, but now there's 10 available toppings instead of 7. So how do we calculate the number of ways to choose the toppings? The same question, just with 10 instead of 7.
Uh,
Yep,
I would say 10 choose 2.
right. Exactly.
So 10 factorial
hmm
or 2
hmm
factorial,
hmm
10 factorial, onto 10 factorial minus 2 factorial.
Right. Not 10 factorial minus 2 factorial, but 10 minus 2
10
factorial.
minus 2.
Yeah.
Okay, factorial.
Right.
That's great. Equal
Yep.
10 times 9,
Yep. Let
10
me.
factorial
Well, no. Okay. Well, we can just do it out. 10 times 9. Sure. This is fine.
times 7 or
hmm
2, 2
hmm
times
Yep.
8 times 7 times 6 times 5
hmm
4. Then we do cancellation.
Great. Cancel everything.
I believe the answer is 45, right?
Yep. That's right.
Nine.
That's perfect. Yep. So we get 10 times 9 divided by 2, which is 90 over 2, which is equal to 45. Okay. Okay, good. So we got 45. That's great. Okay, great. So that's 45. And so now the point is we can use the multiplicative principle, right? So we have 21 ways of choosing the flavors, 45 ways of choosing the toppings, and those are independent. Okay, so can so total total different ways of making a bowl. So total bowls is 21 times 45, which is equal to, so 45 times 20 is 900, so it's going to be 945. So this is going to be the number of ways of doing it. Okay, so for the individual parts, the flavors and the toppings, those are each um, calculated using combinations, and then putting them together, that's calculated using the multiplicative principle. Okay, so you can get very far with just combinations, permutations, and the multiplicative principle. And then sometimes when you don't need when that's not good enough, you need one of these two extra techniques. You need either the additive principle with cases, or you need to count the wrong thing and subtract. So we've seen examples of all of those in the homework today. Okay, so any questions here? Okay, everybody's okay. Okay, so let's do the last problem. So this one nobody gave a solution for. So less than 50 people are at a party. Each person shakes each other's person's hand. So if there are an odd number of total handshakes, then what is the maximum number of people who can be at the party? Okay, and so the hint is we're going to let n be the number of people at the party. And how many handshakes are there in total? Now we're going to try to see if we can find a pattern for which values of n make the number odd. Okay, so each person shakes each other person's hand. 50 people are at the party. So let's say if we let n be the number of people at the party. Okay, so if n is the number of people at the party, okay, then what do we have? So if n is the number of people at the party, then I want to see. Okay, so let's n be the number of people at the party. So how many total handshakes? Well, what is a handshake? Well, what is a handshake? A handshake is picking two people out of the n people. So it's a way of choosing two people out of n. So assuming you don't shake your own hand, it's a way of choosing two people. So the total number of handshakes is n choose two. And what is this? That's n factorial divided by 2 factorial times n minus 2 factorial. And right, it's a combination exactly. And so if you do this, this is n times n minus 1 times n minus 2 all the way down to times 2 times 1. And this is divided by 2, and then n minus 2 factorial. So n minus 2 times n minus 3 all the way down to 2 times 1. And so it turns out you get a lot of cancellation here, right? The ones cancel, the twos cancel, everything here cancels. The n minus 3 cancels with the n minus 3, and the n minus 2 cancels with the n minus 2. And so what you're left with here is just n times n minus 1 divided by 2. Okay, so that's the total number of handshakes, right? If you have n people at a party and everybody shakes each other's hand, then you have a total of n times n minus 1 over 2 handshakes. Okay. So the total number of handshakes is n times n minus 1 over 2. Great. So and this is how we simplify n to choose 2, because you're choosing 2 people out of n. So now the question is, when is this odd? So when is this odd? Okay. Well, whenever you have n and n minus 1, one of them is going to be even and one's going to be odd. Then when you divide it by 2, you need them both to be you need them both to be you need them both to end up being odd to make the whole number odd. So we know that less than 50 people are at the party, and it's asking what's the maximum number of people who can be at the party. So let's just try. Let's try. What happens? Let's see what happens at the highest possible. So what happens when n equals 49? So when n equals 49, we get 49, sorry, we get 49 times 48 divided by 2, which is equal to 49 times 24, and this is even. Right? So that's no good. What about n equals 48? Well, when n equals 48, you have 48 times 47 divided by 2, which comes out to be 24 times 47. Well, that's also even. Okay, so let's keep going down. What about n equals 47? Well, in this case, you get 47 times 46 over 2. That's 47 times 23, right? 46 divided by 2 is 23. And who knows what that number is, but the point is that it's odd, right? Yes, so I see from James, yes, for n times n minus 1 over 2 to be odd, both n minus 1, n and n minus 1 and 2 must have no common factors other than 1 after dividing by 2. So that means it's going to result in an odd integer, which means n times n minus 1 must be equal to 2 times an odd number. And then this is true, that n times n minus 1 must be of the form 2 times 2k plus 1 equals 4k plus 2 for some integer k. That's all great. When is that actually going to happen? Well, in this case, the fastest, most efficient way is probably trial and error. So we saw that it doesn't work for 49, it doesn't work for 48, it does work for 47. So it turns out that the answer here is actually 47. This is the answer. 47 is the largest number for which you get an odd number of handshakes. Okay? If you want to, and I think I'm not going to get into this now, you could try to find in general when is this going to be true. And in general, what's going to happen is that if n is something that gives a remainder of 1 when you divide it by 4, or that gives a remainder of 2 when you divide it by 4, then you're going to get an odd number of handshakes. Whereas if n gives a remainder of 3 when you divide it by 4, so sorry, if n gives a remainder of 2 or 3 when you divide it by 4, you're going to get an odd number of handshakes. If n gives a remainder of 0 or 1 when you divide it by 4, that's like 49 times 48 here, then you're going to get an even number of handshakes. Okay, so it turns out, so that's a good exercise to try to prove that. But to answer this question, you don't need to prove that, right? So to answer this question, all that you need is to just do a little bit of trial and error. What's the largest there can be? Well, 49 doesn't work. 48 doesn't work, but it looks like 47 works. Okay, so 47 is going to be the largest number of people you could have at the party to make sure that it's an odd number of handshakes. And the key here is to just know, how do you get an expression for the total number of handshakes? And the total number of handshakes is n times n minus 1 over 2. It's basically it's between one person, you have n choices. The second person, you have n minus one choices, and then you divide by two because it doesn't matter which order you pick them in. If you pick person A and then person B, that's the same as picking person B and then person A. It's the same handshake. Okay. All right. So any questions about this exercise? Okay. All right. Okay. So no further questions. Okay. I think that's enough for homework. Let's at least do something new today. So, all right. So we're finishing with combinatorics and we're moving on to a probability unit. Okay. So we're going to talk about probability this week and next week and maybe the week after also. We'll see. Or maybe only these 2 weeks. Okay. So what is probability? Probability is the study of how likely events are to occur. And a good brief reference for this topic is if you look at The Art of Problem Solving, this textbook that I sent, then if you look in chapter 26, it really says statistics and probability, but it's mostly about probability. Okay, so volume 1, chapter 26 is mostly about probability. And the reason these two things are together is that lots of probability questions can be solved similarly to combinatorics questions. There's a lot of the same ideas that go into both of them. And the key idea when we calculate probability, the key idea is that if all of the outcomes of an event are equally likely, then the probability of something occurring, the probability of some particular thing A occurring is the number of outcomes where A occurs divided by the total possible number of outcomes. So the number of outcomes where A occurs and then divided by the total possible number of outcomes. Okay, this is how you calculate a probability. And often what happens is that counting these outcomes is itself a combinatorics problem, and you can treat this combinatorics problem with the techniques of our last 2 sessions. Okay? So counting these outcomes is something that we can treat using, you're going to need to count the total number of outcomes where something occurs, and you're going to need to count the total possible number of outcomes. And in the way that you can count them is by using combinatorics. Okay, using these techniques that we have before. So often the probability questions build on the combinatorics questions in order to make everything be able to be solved. Okay, so let me state this a little bit more formally. So more formally, suppose that there are n equally likely possibilities for how an event can happen, and that m of these possibilities we count as a success. Then the probability of success is given by m divided by n. Okay, so it's the successes divided by the total possible outcomes. And as a matter of notation, if A is the particular event that we want, then we write P of A for the probability of success. And as a probability, it's always going to be a number between 0 and 1, right? Because at worst, it has no possibility of success. That would be yes, where n is not equal to 0. Sure. So at worst, it has no possibility of success at all. That will give a probability of 0. And at best, every possibility is a success, and that gives you a probability of 1. Basic example would be if you roll a standard die that has 6 sides, then the probability of getting a 2 or a 5 is 2 out of 6, or in other words, 1 out of 3, right? Because the 6 is total possible outcomes, right? That would be 1, 2, 3, 4, 5, or 6. And the 2 here is the possible number of successes, right? Which is the success in this experiment is whether you're going to get a 2 or a 5. Okay, so 2 successes out of 6 possible outcomes. So the probability of getting either a 2 or a 5 is 2 out of 6, and that's a fraction, so you can reduce it to 1/3. Okay, so this is standard formulation of discrete probability. Okay, any questions so far? Okay, so let's look at an example. So suppose that a 4-digit number is chosen at random, meaning the first digit is not 0, so it's a 4-digit number. We don't allow the first digit to be 0. And so then the question is, what is the probability that all 4 digits are distinct? Well, we have to go back. What do we have to count? We have to count the number of successes, and we have to count the number of total possibilities. So number of successes equals the number of 4-digit numbers with all digits distinct. Okay. And this is not so hard to calculate because choosing these digits is independent, right? For the first digit, we have 9 choices because it can't be a 0. We did this question already a couple of weeks ago. Maybe we did it with a 5-digit number, but it's the same thing. So the first digit, we have 9 choices because there can't be a 0. For the second digit, well, we've already chosen a digit, so we have 9 left. So there's 9 choices. For the third digit, we've already chosen 2 digits, so there's 8 left to choose. So we have 8 choices. And for the fourth digit, we've already chosen 3 digits, which means there's 7 that are still available. So we're just going to have 7 choices here. Okay, so we have 9 times 9 times 8 times 7. And that's going to be equal to 4,536. Okay. Now we can have the total number of possibilities well, that's just the number of ways of choosing a 4-digit number, right? So the total number of possibilities is just equal to the number of 4-digit numbers. Okay, and now with no conditions at all, right? So for a 4-digit number in general, your first digit you have 9 choices because it can't be a 0. And then for all of your other digits, you have 10 choices because you can choose any digit you want. So 9 times 10 times 10 times 10, and this comes out to be 9,000. Okay, so what is it? So the probability of success is just the number of successes, 4,536, divided by the number of total possibilities. That's 9,000. So I'll just write this here, number of successes divided by the number of possibilities. Okay. And there you have it. And if you want to, you can make this 4,536 divided by 9,000. You can make it a fraction if you want. This turns out to be exactly equal to 0.504. Okay. Okay. So what this is telling you is that there's a little bit over a half a chance. So if I pick a random 4-digit number, a little bit more than half the time, it will have all of the digits distinct. And 50.4% of the time, it will have all the digits distinct. Okay, because the number of ways to have all the digits distinct is 4,536, which is a little more than half of the total possibilities. Total possibilities is 9,000, so 4,536 is a little bit more than half of that. Okay, so this is a probability problem, but it's really just a combinatorics problem in disguise. Okay, to calculate a probability, you're just calculating a numerator and a denominator, And both of those are being calculated using combinatorics, using the standard multiplicative principle for independent events in combinatorics. Okay, you're just calculating how to choose these digits and how many choices do you have. Okay, and the only thing that makes it a probability question instead of a combinatorics question is this step at the end where you divide the answers. Otherwise, it's really just two combinatorics questions. All right. Anything unclear here? Okay. All right, no questions. Good. Okay. So what's a law? So in probability, you have a multiplicative law for independent events just like you do in combinatorics. So we have a theorem here which is called the law of independent probability. So this says suppose that A and B are two independent events. What does independent mean? It means that the probability of B happening is not affected by whether or not A happens. Or vice versa, the probability of A happening is not affected by whether or not B happens. Then, how do you figure out the probability of A and B both happening? Well, what you do is you multiply the probabilities together. So it's the probability of A times the probability of B. So sorry, before I go on further with this, can any number be chosen? Any four-digit number can be chosen in this case, but a four-digit number by definition doesn't start with a zero. So you only have 9 choices for the first digit, and then you have 10 choices for each of the next digits. So the total number of four-digit numbers is 9,000, and the number that have all digits distinct is 4536. So the probability, if you choose any four-digit number, that the numbers will have all digits distinct is 4536 divided by 9,000. That's going to be 504. Okay. 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 So let's go back here. Okay, so this law of independent probability says that the probability of two independent events both happening is the product of the probabilities of each individual one happening. And we should think of this theorem as being the probability analog of the multiplicative rule for independent events in combinatorics, right? Because suppose that, so what do we have? So what is the probability that, A and B both happen? Well, what's that going to be? That's going to be the number of ways A and B both happen over the total number of possibilities for the events. Okay? And what is the number, if A and B are independent, then what's the number of ways that A and B can both happen? Well, this is equal to the number of ways A can happen times the number of ways B can happen. Number of ways B can happen. That's the numerator. And the denominator, what's the total number of possibilities for the events, is the number of possibilities. Sorry, this is a little small. For A's event times the number of possibilities for B's event. So what I'm doing here is a proof. So what's the probability that A and B both happen? Well, it's the number of ways A and B can both happen over the number of possibilities for the events. But the events are independent. So the number of ways that A and B both happen is the number of ways A can happen times the number of ways that B can happen. This is the fact that this is true. This is exactly the multiplicative principle in combinatorics. This is the multiplicative principle in combinatorics. And what are the total number of possibilities? It's the number of possibilities for A's event times the number of possibilities for B's event. So now what happens? What is this quantity over here? We have the number of ways that A can happen divided by the number of possibilities for A's event. That's exactly equal to the probability of A. And now what about this over here? Let me use a different color. We have the number of ways that B can happen divided by the number of possibilities for B's event. That's exactly the probability of B. Okay, so this is the proof. Okay, so the probability that A and B both happen, we saw that we can write it as this fraction, the number of successes divided by the number of possibilities, but each of these breaks up into a product by using the multiplicative principle in combinatorics, and in the end, this simplifies to the probability that A happens times the probability that B happens. And the reason you can break it up into these products is exactly because the events are independent. So you have this multiplicative principle in combinatorics for these events. Okay, they're independent events. Okay, so this tells us that the probability that A and B both happen is the probability that A happens times the probability that B happens. Okay, and this is what we call the law of independent probability. So just like combinatorics, when you count things, you multiply in order to count multiple events. In probability, you also multiply to count the probability that two independent events happen. Okay, any questions on this? Okay. Okay, so let's see an example of this. Okay, so we'll do a very easy example of this. If I roll 3 dice, what is the probability that all 3 numbers are odd? Well, clearly, the 3 rolls are independent. Clearly, the 3 rolls are independent. Okay, so each roll, the probability of an odd number is, well, we have the total number of ways of getting an odd number. That's 3 ways, right? Because you can get a 1, a 3, or a 5, divided by the 6 total possibilities, because you can get a 1, 2, 3, 4, 5, or 6. And this 3, 6, in other words, is 1/2. So each roll, the probability of an odd number is 1/2, and now you've got 3 independent rolls, so the probabilities are going to multiply together. So the probability that all 3 rolls are odd, this is equal to 1/2 times 1/2 times 1/2 using the law, or maybe let me just write this out. 1/2 times 1/2 times 1/2, which is equal to 1/8. using the law of independent probability. What? Okay, so this is the most basic example of this law of independent probability. Each individual event is 1/2. The chance that all three of them come out to be odd is 1/2 times 1/2 times 1/2. That's 1/8. Okay, any questions on this example? Okay, good. All right. So, last thing I want to do today, we'll do a little more probability next week. So, multiplicative probability, what happens with non-independent events? So, oh, sorry. Suppose that A and B are two events. This is very important. I don't want to assume that they're independent. So, we'll assume that A and B are just two events that are not necessarily independent. Okay. Okay, so let's say that we have two events that are not necessarily independent. Okay, well then the chance that A and B both succeed, you can calculate it as the probability that A succeeds times the probability that B succeeds given that A succeeds. So this is what this notation means here. P of B given A means the probability of B succeeding given that A succeeds. This is important enough that I'm just going to write it again. Probability of B given A, by definition, this means the probability that B succeeds given that, so given that given that A succeeds. Okay. So what does this kind of makes sense. I'm not going to give a formal proof of this, but what's the idea? Well, how do you know that A and B would both work? Well, you need A to happen, and now given that A's happened, you also now need B to happen. So when you need two events to happen, you generally multiply the probabilities. I should mention that if A and B are actually independent, then the probability that B succeeds has nothing to do with whether or not A succeeds. So if they are independent, so this is just a remark, right? So if A and B are independent, then the probability of B given A is just the same thing as the probability of B. Right? So if A and B are independent, then the probability of B doesn't depend on the probability of A. So the probability of B succeeding given that A succeeds, well, who cares that A succeeds? It doesn't matter. That's just the same as the overall probability of B. So what this shows is that if you have two independent events, this formula just becomes P of A times P of B, and you get exactly what happens here is that you recover the law of independent probability. Okay. So in this case, P of B given A is just P of B, and you recover the law of independent probability. So if you haven't done this over here, this is called a conditional probability. Okay, the probability that B happens given that A happens. Okay? So if you haven't seen conditional probability before, then this is maybe a little bit confusing, but we'll do an example that will hopefully make it clearer. And what I want to mention is that the real applications of probability, when you want to see actual applications of probability applied in science, it is almost always conditional probability that's being used. So next week, we're going to talk about probably the most important law in probability, which is called Bayes' law. And Bayes' law is extremely important for understanding scientific studies. And Bayes' law is fundamentally about conditional probability. Okay, so we're gonna talk about that. We're gonna talk about that next week. But I want to just give today, with our last example that we're going to do now, just this introduction to conditional probability. So the way in general that you can get the probability that A and B both succeed is the probability that A succeeds times the probability that B succeeds given that A succeeds. Okay? So let's do an example. So even before I read the example, I'm just going to rewrite the rule so that we don't have to do it. P of A and B is equal to the probability of A times the probability of B given A. Okay, so now let's read the question. So the question says a set of 10 cards numbered 1 through 10 are in a box. Adam takes one of the cards, and then Benjamin takes the second card. What is the probability that Adam's card is even and Benjamin's card is odd? And why are these events not independent? So maybe let's answer the second question first, right? Well, why are they not independent? Well, the point is, if Adam takes an even card, then it's more likely that Benjamin's card is odd because Adam has taken out one of the even cards. So now there's more odd cards left. Whereas if Adam's card is odd, then it's a little less likely that Benjamin's card is odd because Adam's already stolen one of the odd cards. So whether or not Adam's card is even affects the probability of whether or not Benjamin's card is odd. If Adam takes an even card, it's more likely for Ben's card to be odd. If Adam takes an odd card, then it's less likely for Benjamin's card to be odd. So that's why these events are not independent. So we can't just use the law of independent probability. If we had the law of independent probability, then Adam's card being even would be 5 out of 10 or 1 out of 2, and Benjamin's card being odd would be 5 out of 10 or 1 out of 2. And what that would mean is that we'd have the total probability would be 1/2 times 1/2, which would be equal to 1/4. But as we're going to see, 1/4 is not the correct answer here. Okay, so let's work this out. So let's let A be, we want both of these events to happen. A is going to be Adam's card is even. Okay, and B is Benjamin's card is odd. Okay, so A is going to be Adam's card is even, B is going to be Benjamin's card is odd. So we'll first figure out P of A. So I'm going to use the law of, I forgot what I called it. We're going to use the law of non-independent multiplicative, or maybe I'll just say use the formula. We're going to use the formula above. Okay. Well, first we need to know what's P of A, probability that Adam's card is even. That's not so hard because there's 5 even cards divided by 10 total cards, right? These 5 even cards are 2, 4, 6, 8, and 10. And the 10 total cards are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, that writing is small. So that's 5 over 10, or in other words, 1 over 2. Okay. So that's fine. That's 1/2. Now, what is the probability of B given A? So this is saying, given that Adam's card is even, what is the probability that Ben's card is odd? Okay. Well, If Adam took an even card, how many odd cards are left for Ben? Well, there's still going to be five odd cards because Adam took an even card, so he didn't take one of the odd cards. So there's going to be five odd cards left. There's still 1, 3, 5, 7, or 9. But now, how many total cards are left for Ben? Well, Adam already took one of them. He already took the even card. So that means Ben doesn't have 10 choices anymore. Ben only has 9 choices because Adam already took the even card. So in this case, it's going to be 9 because I can't tell you exactly which 9 they are, but it's because Adam took an even card, or is that he took a card at all, right? Adam took an even card, which means all of the odd ones are still left for Ben, but there's fewer cards left. So by taking an even card, Adam made it more likely that Benjamin's card was going to be odd. More likely because 5/9 is bigger than 1/2. Adam made it more likely that Ben's card is going to be odd. And so what this tells us is that the probability that A and B both happen is actually 1/2 times 5/9, which is 5/18, which is roughly, you can do this in percent if you want, this is roughly 27.3%. I think that's right, right? 5 divided by 18. I'm sorry, 20, not 27.3%, 27.8%. Okay. I mean, 27.8%. Okay, any questions here? So let me just box these so that they're easier to find. We have the 1/2 and we have the 5/9, and then when we multiply them together, we end up getting this 5/18, or if you want to write it in percents, that's 27.8%. Okay. So in order to calculate this probability that they both happened, we had to use that they're not independent. So we had to use this more complicated law. That they both happen is the probability of A times the probability of B given A, or B dependent on A. Okay. So I think that's a good thing to finish on today. Let me mention the homework. So there's going to be 3 homework exercises. So first we have a blue urn contains 4 black marbles and 2 blue marbles. A black urn contains 4 black marbles and 11 blue marbles. 1 marble is taken at random from each urn. What is the probability that both marbles are blue? So this is going to be a straightforward multiplicative principle for independent probability. 2, a box contains 3 red balls and a green ball. If 2 balls are chosen from the box, what is the probability that the first one is red and the second is green? This is going to be exactly using this later formula. Okay, and now number 3, we have suppose that 2 dice are rolled. What is the probability that the sum of the 2 numbers is odd? Okay, so that one I'm actually not really going to tell you how to do it. I'm going to let you just think about this one for a little while, and we'll spend some more time on it next week. Okay? And so thank you as always for your attention. Next week on December 11th, we're going to continue our study of probability with what's called the law of total probability and Bayes' law. And what we're going to do with Bayes' law is we're definitely going to see some applications here, like real applications, not just dice and marbles. So we're going to see some applications here for Bayes' law, in particular important applications for understanding scientific studies. Okay, are there any questions? Okay, all right. If there's no further application questions, then one final reminder to type your name in if you haven't done it already, And then I will send out the notes and I'll send out the recording later tonight. Okay? All right. Thank you very much for your attention. Have a great weekend, and I will see you next week. Bye, everyone.